So let's try to solve this exercise here. We want to find the unconditional density of x, and just let us consider the density for values greater than 0, mostly because x given w is gamma distributed. So that means that is very unlikely that x takes values smaller than 0. So let x be greater than 0. Then the unconditional density fx of x, well, that is equal to the integral from minus infinity to infinity of this thing here. So the conditional density of x given w multiplied by the density of w. And this, as stated before, well, the conditional density of x given w is the gamma density with parameters beta and w, and the density of w is the gamma density with parameters alpha and theta. So we can just substitute the expressions for those densities in, and since these densities live on the positive half axis, we can plug in 0 here, and then we have, well, what do we have? We have gamma of beta down here, and then I think we have w to the beta, and we multiply by x to the first parameter minus 1, multiplied by e to the minus second parameter multiplied by x. So this is the conditional density of x given w. Now the next part is the density of w. So when we're looking at the density of w, w is the argument that we need to plug in. So here we still have the parameters. Down below we have gamma of alpha, and then up here we have theta to the alpha, and then the argument is w, and we take that to the alpha minus first power, and then we take e of minus theta w dw. So that's a pretty long expression, but fortunately we can take quite a lot of stuff outside of the integral sign. So anything that does not rely on w can be taken outside of the integral, and that is stuff such as x to the beta minus 1, and theta to the alpha, and gamma of beta, gamma of alpha, and I guess that is pretty much it. So now what do we have inside? Inside here we have the integral from 0 to infinity of w to the beta plus alpha minus 1 multiplied by e to the minus parenthesis theta plus w, theta plus x multiplied by w. And the reason why I want to collect these two, well, is because the other thing was just wrong. So here inside this integral, I have something that I want to evaluate the integral of. And the first thing that I can think about is, well, here I have the argument to a power minus 1 multiplied by e to minus something multiplied by the argument. And this looks suspiciously like a gamma density. And in fact, I can actually multiply some things on there that makes it look even more like a gamma density. So this is a trick that we use pretty often, that we try to multiply stuff onto things to make them look like densities, so that when we integrate those, then we just get 1, because then we integrate the density. So what do we need multiplied onto this expression in order for it to be a density? Well, in the gamma distribution with that we're interested in here, the parameters we would need would be, well, the first parameter should be beta plus alpha, and the second should be theta plus x. So that means that we will need to have a constant where we divide by gamma of beta plus alpha, and above here we need theta plus x to the beta plus alpha. And when we have that, then that means that this is exactly the density for the gamma distribution with these parameters evaluated in W, and this entire thing just evaluates to 1. So however, we have multiplied with this constant here, so we have essentially changed our expression. So in order for nothing to change, we should divide with that same constant as well. And that is exactly what we will do. So we will divide by this constant, which means we multiply by its inverse, in which case we get this thing here, theta plus x to the beta plus alpha. And this entire term just cancels out to 0 because here we recognize a gamma density that integrates to 1. So in the end, what do we have left? In the end, what we've got left is this. We have gamma of beta plus alpha divided by gamma of beta multiplied by gamma of alpha, and then multiplied by x to the beta minus 1 multiplied by theta to the alpha divided by theta plus x to the beta plus alpha. And one thing that you might notice if you guys have been looking at the Pareto distribution is that this kind of looks like something that's Pareto distribution like if we only look at this part. And in fact, this density is called the density for the 3-parameter Pareto distribution. It almost sounds like a rap. So this is the density for a 3-parameter Pareto distribution. So now that you've seen this thing, you can just kind of remember that if we have a mixture model where we take x, where we take W and let it be gamma distributed, and then say that x given W is gamma distributed with second parameter equal to the value of W, then we get that x is 3-parameter Pareto distributed.